In this video, I'm going to focus on the concepts related to uniform circular motion. Let's start by defining the motion. We're looking for something moving along the circumference of a circle. I like the Earth as an example because it's doing two things at the same time. The Earth is moving in a big circle around the Sun. That's the circular motion. It's also spinning on its own axis. That's a rotational motion and is something we'll cover in a future video. Know that the word uniform means unchanging. As it relates to circular motion, there are two things that are not changing about the object. It's a constant speed, meaning it's not getting faster or slower, and it's a constant radius. It's not getting closer to or further from the center of the circular path. Here I'm using a satellite to answer a conceptual question. Let's say the satellite is orbiting Earth in a circular path, and if we completed a force diagram for the satellite, we would find a force of gravity on the satellite by Earth and directed at Earth's center. If we use strategies discussed in our one-dimensional dynamics unit, we would take this unbalanced force of gravity, we would make it the net force, and in place of the net force variable, we can substitute in mass multiplied by acceleration. So in looking at this setup, it appears as though the object would accelerate along the line of FG and crash into Earth. So the question is, why don't all satellites crash into Earth if we analyze them in this way? To get started with our answer, let's first say that acceleration, as previously studied, was for linear motion. The satellite is not moving in a straight line. It's moving in a circular path, and therefore we're going to need a new method. What is missing in our analysis is velocity. This satellite is not released from rest. Rather, it is given a velocity tangent to its circular path, and therefore perpendicular to the central force of gravity. So if both of these vectors are present, a central force and a tangent velocity, the object will split the difference between those vectors and move in a circular path. So the two requirements for uniform circular motion are a net force directed to the center of its circular path and a velocity directed tangent to its circular path, which ends up being perpendicular to the net force. Another conceptual idea that warrants a discussion is with uniform circular motion and acceleration. Now, we've already discussed that uniform circular motion means constant speed. So the question is an object accelerating if it moves with uniform circular motion? Now, most students say no because of constant speed, but unfortunately they would be incorrect. To talk about why they're incorrect, let's review a few old ideas. First, acceleration. We defined it as the rate of change in velocity. A second thing to review is the difference between speed and velocity. Do you remember the difference between these terms? Speed only considers how fast an object is going, whereas velocity considers how fast and which direction an object moves. So although speed is constant because we're not getting faster or slower, velocity is not constant. As you move in a circle, you're always turning. Because you're turning, you're changing direction, and because you're changing direction, the velocity is changing. So if you are ever posed with the question, is an object accelerating if it moves with uniform circular motion, you want to answer yes, not because it's speeding up or slowing down, but rather because it's always turning and therefore always changing direction. Let's talk about vector directions for uniform circular motion. We've already discussed that velocity should be tangent to the circle, but it should also be in the direction that matches the overall motion. So for this object that is moving in a circle in a counterclockwise direction, we want to have the velocity on the right side of the circle go up and on the left side down to match the overall counterclockwise motion. Force should point to the center of the circle. We call this force centripetal force, centripetal meaning towards center. And this is like the net force for circular motion. So relate Fc to circular as you would F net to linear. Finally, acceleration. We remember F equals ma. If the force points to the center, the acceleration should as well. Why does it point to the center? Well, imagine we're in this car and we're driving north and we want to turn in a circle. Which direction would we turn the wheel? I think we turn it to the left, towards the center of the circle. So that's the direction we're trying to make the car change, and that's why it's accelerating that way. Let's end with a sample problem. Here we're looking at an object moving clockwise with uniform circular motion. When it gets to position P, represented by the black dot, 3 questions are asked. I'll let you read through them. If you want to pause the video and try these on your own, I'll talk you through each in a minute. We'll start with velocity. We know that it's tangent to the circle and in the direction of motion, so at position P, this would point straight to the left. For acceleration, we know that points to the center of the circle. Position P is at the bottom of the circle, so acceleration would point vertically upwards towards center. For force, there's two reasons as to why F1 is greater than F2. The first thing we can say is that we know centripetal force is like net force, and we want it to point towards the center of the circle. Well, the only way the net force would point towards the center is if the F1 towards center force is greater than the F2 away from center force. The other thing we can do is track the object. Let's say my mouse represents position P and it's coming around the circle, here it comes, and it gets to position P, and it's like, what is it going to do next? If F2 was bigger than F1, it would curl downward. If these forces were equal, it would continue in a straight line. But if F1 was greater than F2, the next thing it would do is turn upwards and complete the circular path.